Hi, so welcome back. So in this lecture, we look at the second order linear non-homogeneous ordinary differential equations. In other words, non-zero input on the right hand side, but with a special kind of input, this is the exponential input. So this is an exponential term with a coefficient in front, that's a constant. So we solve the particular solution for this kind of a second order linear differential equation with an exponential input. Now, in the previous lecture, we have solved a part of it. So when this quantity, this factor a, if you bring it down here and instead of x double prime, you put a square, instead of x prime, you put a. If this factor here is non-zero, then we had shown that the particular solution for that in that condition would be this value, this function here, a by this non-zero factor, multiplying that would be exponential of small at, this right hand side. Okay. All right. Now, obviously, this is valid when this factor, this value here is non-zero. But if it is zero, then we run into trouble. Okay. Now, before that, I just want to clarify that. So, what do we mean when? So, right now we are in this lecture. We are going to investigate what xp will be, the particular solution of this differential equation will be when this value is actually zero. A square plus ba plus c is equal to 0. What would this be? This is what we are going to investigate. Now, to say that this is equal to 0 is the same as saying that a is a root of the auxiliary equation of the homogeneous form of this differential equation. Okay, I said a lot of things there, so let's go one by one. So what's the homogeneous form of this equation? It's just making the right hand side 0 without any external force on the system. So the homogeneous form of this differential equation will be x prime plus bx prime plus cx equals 0. That's the homogeneous form. Okay, now this is a homogeneous differential equation then, second order linear differential equation. What's the auxiliary equation of this homogeneous second order linear differential equation? That would be some variable m square plus this b m instead of x prime and c equals 0. That's the auxiliary equation, where we had always assumed that the two roots of this, going by the terminology that we have used in this series, the two roots of this quadratic equation will be m1 and m2, the two roots, okay, of this quadratic equation. In fact, because you have these constant here, m1 we have always assumed to be minus b by 2, the positive of this square root term, the discriminant term, and m2 we have assumed to be minus b by 2, the negative of the square root term. Okay, this is what we have, the notation that we have been using in this series. So, all right. Now, so what did I say? I said that assuming that this value is equal to 0 is the same as saying that a is a root of this equation. Okay. Now, if a is one of the roots, is a root of this quadratic equation, then it must be either m1 or m2 or both. In that case, m1 and m2 are the same, because m1 and m2 are the two roots of this equation. So to say this is the same as, so saying that a square plus ba plus c is equal to 0 is the same as saying that a is either m1 or it is m2. Actually, without loss of any generality, that's the phrase that we use in mathematics when we don't want to distinguish between these two possible candidates. So a can be either m1 or m2. We don't want to distinguish. Let's say for our purpose that a is equal to m1. Okay, this is without loss of any generality. That's the phrase that is used. In other words, you could have assumed m2, somebody else could have assumed a equals m2, and that person would have gotten the same result as we would. assuming that it is M1, okay? So without loss of generality, we will assume that A equals M1 and we will proceed from there on. So this is the same as saying that A is one of the roots, M1, of this. Okay, let's just write that down here because I want to rub this part of the board. Okay, now we will therefore find xp, the particular solution of this, using whatever the conditions are. Okay, so now the condition in which we have to find this particular solution is this. So this is 0. That's the problem, because we can't put, if it is not 0, this particular solution is valid. The problem becomes when this is 0, because we can't have 0 in the denominator. So we assume, this is the trick that we always use, we don't assume that it is exactly equal to 0, but very close to 0. That we take the limit approach. So we assume that this is not exactly 0. When is this not exactly 0? When A is not exactly M1. If A is exactly M1, then this would be 0, because M1 is a root of this. So what we do is, we don't assume that A is equal to M1. Instead, we assume that A is very close to M1 or approaches M1. In other words, as A goes to M1, this actually goes to 0. When it is exactly M1, because M1 satisfies this will be exactly equal to 0. Okay, so this is the case. When A is equal to M1, this is 0. But as A approaches M1, this approaches 0. Okay, so we work this particular solution out, assuming that none of these are exactly equal signs, but they're all approaching their, respective limits. All right, so when this is not equal to M1, but very close to it, well, this is valid, because this is close to it means this is not exactly 0, but close to 0. So this is valid. So we make a start here to find the particular solution. We don't have this equal to 0 anymore. So we say that this is the solution. Capital A, e to the power small at by a square plus ba plus c. Well, now we make a certain adjustment here and we invoke the result, the all-important result that we have used or we have found out in the previous lecture, was that if you have a particular solution, this is a particular solution in the condition that this is not equal to 0, you can take away or you can add a certain weight of the homogeneous solution of this the differential equation, and it would still be a particular solution. So you can refer back to the previous lecture where we have actually established this result. So if M1 and M2 are the two roots of this quadratic equation, the two homogeneous solutions satisfying the homogeneous form of this differential equation, that is with 0 right hand side, are e to the power m1t and e to the power m2t. Okay? Well, again, how these come, you have to go back to the lectures where we have covered them. So, and these are the two homogeneous solutions, two possible homogeneous solutions of the homogeneous form of this differential equation. Let's call them xh1 and xh2, just to give them some name. So, just let me quote the result again. So, what did I say? I said that this is a particular solution. I can take away, or I can add a weight of this, any of the homogeneous solutions. So I'm going to use e to the power m1t. I'm going to add a weight of this, which I will use the same but with a negative sign. So I'm taking away a weight of the same weight as a, capital A by small a square plus ba plus c. And this is still a particular solution. That's the result we have proven in the previous lecture. Well, if you want, it's no more the particular solution we started with, which was only this. So if you want, you can make it particular prime just to give it a different name, but just because we don't want to confuse or use too many notations, I'm going to keep calling it XP because I know that this is a particular solution. In other words, this will satisfy this equation. But of course, we are working this out in the limit that A approaches M1. So this we are working this the XP out, the particular solution out, where A approaches M1, and finally we make A equal to M1 and see where the result goes. That's the roundabout route we are taking because we can't straight away put A equals M1 because that would give me the 0 in the denominator. So this is the route that we take. Now let's regroup things a bit. So what do we have? So you have in the numerator, capital A is common. You have e to the power at minus e to the power m1t divided by a square plus ba plus c. All right, now as a goes to m1, a square plus ba plus c goes to 0, so the denominator goes to 0. And as a goes to m1, here a approaches m1, which is the same as this. So this quantity here goes to 0. So this is the famous 0 by 0 form of L'Hopital's rule as a goes to m1, and we can invoke that rule, which is to differentiate now both the numerator and the denominator with respect to a, because a is the variable going towards m1. So let's apply L'Hopital's rule here. Differentiate the numerator and the denominator. Let's do the numerator. Let's do the numerator first. Differentiate that with respect to a, the variable. The capital A is a constant. I'm differentiating this with respect to a. So t is the constant, so that comes down. E to the power at remains as it is. This is a constant with respect to small a because there is no small a in here. So this gives me a 0. So I just get only this much from the numerator. From the denominator, if I differentiate this with respect to small a, I get 2a plus b. And that's what I get. Now I can put a equals m1 here as long as 2m1 plus b is not equal to 0. So this would be capital A e to the power m1t by 2m1 plus b. This is when 2m1 plus b is not equal to 0. And that would be the particular solution. If this condition is held, if this condition is satisfied that 2m1 plus b is not equal to 0, then this would be the particular solution in the case that this quantity is 0. And that's what it is. Okay? So let's just write that down here. I am going to rub this part out. I'm going to list the possible particular solutions on the right hand side like here. This was the case, first case when this is not 0. The second case when this is equal to 0. We have the particular solution being equal to capital A. Oh, there's a t. Don't forget the t here. There's a t in there, okay? So t e to the power m1t by 2m1 plus b. This is when a square plus ba plus c is equal to 0, but 2m1 plus b is not equal to 0. That's the case. Well, of course, a is equal to m1. That's the case we were studying. Saying this is the same as a being equal to m1. We have the equivalent sign here. We've shown that. So we don't want to keep m1 here because we've written this result in terms of small a, so we will change that. It's just that we made a and m1 equal by a roundabout way, making one approach the other. But really we were investigating this case when a is equal to m1. So in my result here, I'm not going to keep m1. My result will be in terms of small a. So let's just write that. So the result really is this. When this is 0, but this part is not 0. Okay. But there is trouble. There's there's still trouble lurking here, because this is true when this is not 0. In other words, this is not 0. As I said, A and M1 are the same. As long as this is not 0, this is valid. But what if this is equal to 0, or this is equal to 0? Then again, we are back to the same problem of having a 0 in the denominator, and we have to study the case one more time. So let's do that. Let's do the last, this will be the last case where this will be equal to 0. Okay. I'm just rubbing this out. And now we will study another case where this is 0 and this is also 0. This is 0 and this is also 0. 2a plus b is also 0. What about that? When this happens, what will be my particular solution? Well, so first of all, let's go one by one. Because this is 0, we said that A will be a root of the auxiliary equation. So we had assumed that A was equal to M1 without loss of any generality. So let's stick to that. When A is equal to M1, we have another added condition here. So this means that really 2M1 plus B is equal to 0. This is the case that we are studying. Now, what is 2M1 plus B equal to 0? This really means that M1 is equal to minus B by 2. Well, what if M1 is equal to minus B by 2? It just means that this square root part is 0. This discriminant here is 0. If this is 0, this is 0 because they're the same. So both M1 and M2 will be equal to minus B by 2 and they're equal. That's the case of resonance that we have studied in details. So in the case that M1 becomes equal to minus B by 2, which is this case, we have M1 equal to M2 and they're both equal to minus B by 2, which is the case of resonance. And in that case, the homogeneous form of this differential equation was given by, well, there were two different homogeneous solutions to this homogeneous form of this differential equation. One was e to the power m1t, and the other was t e to the power m1t. These were the two possible solutions, different solutions of the homogeneous form of this differential equation with a 0 on the right hand side. In the case of resonance, when M1 and M2 were both the same. So this was, for example, XH1 and this was XH2. The two homogeneous solutions of the homogeneous form of this differential equation. You can again go back to the previous lectures where we have established this. So now, okay, with that setup, let's see what we can do. So this is the trouble here. As long as this is not 0, this will be my particular solution. Okay, as long as it's not 0. This is not a trouble anymore because we have established the result, particular solution, when this is equal to 0, but it's not equal to 0. So let's assume that this is not equal to 0, but very close to 0. The same trick we have applied before. So let's assume that 2a plus b is not equal to 0, but very close to 0 or approaching 0. In which case, a is approaching minus b by 2, which really is m1. So studying the case, this limiting case when 2a plus b is going to 0 is the same as studying the case when a is going to m1. Back to what we had done before. It's the same case. A going to m1 is the case, that limiting case that we are doing. So in this case, when this is not 0 but close to it, we know what the particular solution is. It's not 0. So this is correct. This is valid. So xpt, particular solution, is of this form. Capital A t e to the power small a t divided by 2a plus b. Well, we do the same thing as before. We use some kind of an intelligence like we did before. And we take away a weight of the same weight as this, capital A by 2ab, of a homogeneous solution. Now we have two possible homogeneous solutions. One was this, the other was this. We will use this one, t e to the power small m1t, because we have t e to the power at here. That's the intelligence that we are using. It's very easy actually. And as I said, if you take away a part of the homogeneous solution from the particular solution, which is this, it still remains a particular solution. So we're not changing anything except that you can give it a different index, but we don't want to. So we're going to find out this thing, by this result, by this adjustment. And we are obviously doing the case when this is going to 0 or a going to m1. That's what we are doing. Okay, this is the same as 2a plus b approaches 0 is the same as a approaches m1. So let's just do that. So we have limit a going to m1. Well, let's group things here. So we have, from the numerator, we have capital A small t common. So again, we have e to the power small a t minus e to the power m1t, which will remain inside the brackets. And we have 2a plus b here. Well, what happens here is as a goes to m1, as I said, 2a plus b goes to 0. So we have a 0 here. And as a goes to m1, this goes to m1. And again, this approaches 0 because you have e to the power m1, almost m1, minus e to the power m1. That's 0. So again, the 0 by 0 form of L'Hopital. And we have to invoke that once more. So let's just do that. So limit a going to m1, differentiate both numerator and denominator with respect to a, because that's the variable. Let's do that for the numerator first. Capital A and small t are constant with respect to small a, so they remain what they are. For this one, small a is the variable, t is the constant, so that comes down. And you have e to the power at minus, well, this is constant with respect to small a, that's 0, so we don't get any contribution from that, so you get a t square here, capital A t square e to the power at divided by, what happens here, if you differentiate this with respect to a, you just get a 2. Well, this is definitely not in the 0 by 0 form anymore, because in the denominator you have a 2, so we are safe. So we can definitely put a equals m1 here without any problems. So let's just do that. So this will be a t square e to the power m1t by 2. And that's what the result is in the limit, in the case that 2a plus b is also equal to 0. So let's just write that down. Well, that's the third case when xp, well, the particular solution in this case will be capital A t squared e to the power m1t by 2 when a square plus ba plus c is equal to 0 and when this is also equal to 0, 2a plus b is also equal to 0. Well, of course, a is equal to m1. Because this is the case where both m1 and m2 were the same. This is the case of resonance. m1 and m2 are same. And we've assumed that a was equal to one of the roots, m1. So really, a is equal to m1 is equal to m2. So a is equal to m1. So I want to write, just like before, I want to write the result in terms of a. And that's what you get. So here it is on the right-hand side. The three possible particular solutions of this differential equation, second order linear non-homogeneous differential equation with an exponential input, and depending on how a, small a, capital B and C, how they combine and they play out, you have the different particular solutions in the three different cases. I think we will finish this lecture here. we will take things forward to a general solution of such differential equations in the next lecture. Thank you.